This is so much fun. And it's so nice to see so many men amongst us. Usually Women in Philanthropy is 30 to 50 women, and here we are together. This is fantastic. I'm Aggie Hirschberg, President of Women in Philanthropy at UCLA. This is an organization that started 20 years ago by a handful of women, some of who are here. And today we're 1,400 and have raised over $161 million for UCLA for our various projects.
That's great.
So today, this is a collaborative event between three of us. Women in Philanthropy first, UCLA Henry Samueli School of Engineering, and Applied Science, and then the UCLA School of Arts and Architecture. Information about all three of us is out in the lobby, so you can take us home if you like. I have some script to say about our presentation today, but I'm a novice. I'm here to learn just like you are here to learn, and I'd much rather hear the introduction from Dr. Wu than from myself. So, but I would like to talk a little bit about Dr. Wu before he comes up. He is the chair of the Department of Bioengineering and in Engineering, and chair of the Division of Advanced say it for me. See, there you go. Chair of the section of Biomaterial Science, director for UCLA Weintraub Center for Reconstructive Biotechnology in Dentistry. Dr. Wu has dual appointments both in the engineering school and the School of Dentistry. Isn't that crazy? He is the chair of the Department of Bioengineering and Engineering and the chair of the Division of the Advanced Prosthodontics, chair of the section of Biomaterials Science, director of UCLA Weintraub Center for Reconstructive Biotechnology in Dentistry. He's a member of the California Nano System Institute. It goes on and on and on. And I think what's important when I read your bio is that Dr. Wu is among a handful of dentist scientist awardees who maintain practices of the highest level and at the same time running a world-class research program. So welcome to our event, and Dr. Wu, I turn it over to you.
Well, thank you for inviting us. On behalf of the panelists, we're really privileged to be here to spend a couple of hours with you. And I want to thank you all for supporting UCLA. One of the premier public education universities in the world. Today, I am honored to be introducing some of the panelists. So let me go through the sequence of events. After a brief introduction, I'm going to speak about 5 minutes, just general 3D printing. Okay, some of it you might have heard before, some of it might be new. And then the panelists will each have a chance to come up for 5 to 7 minutes and have their own presentation. Some of it will be repeats, okay? Some of them are worth repeating, so I hope you enjoy it. The first panelist is Yulia Koena, who is a lecturer in the UCLA Department of Architecture and Urban Design. She's a faculty in the UCLA Super Studio, where they do this amazing interdisciplinary teaching, joining forces of industry, from entertainment to NASA, to really work on how to train the future architects on designing. And she will give you a wonderful talk on that. She recently won the Rising Star Award in the 2014 3D Print Show, which is one of the hardest shows in this field. She earned her master's in architecture in the University of Applied Arts in Vienna, Master of Science in Architectural Association in London. She has many, many awards, and if you look at her, if you Google her on the internet, you will see that she's quite accomplished. Our second panelist, Professor Xiaozhong Li, joined us from Wisconsin. He earned his MS degree in Ohio State, the Ohio State University, PhD from Stanford in mechanical engineering. He joined us as the Raytheon Chair in manufacturing in the Department of Mechanical and Aerospace Engineering in the engineering school. His expertise is generally classified as science-driven manufacturing. He is one of the foremost experts in the field of nano and micro manufacturing. So, you know, in my lab, we make things really small, but we just make one and we're happy. He focuses on how to make a lot of it, okay? He's won many awards from junior faculty all along to his current status. He won the Outstanding Young Manufacturing Engineering Award, National Science Foundation Career Award, which is given to only the top few % of engineers in the country. He's won all kinds of manufacturing awards, Sir Humphrey, Howard Taylor, and the list goes on. And he's going to give us an amazing talk on how we can make things reproducibly that are tiny, okay? And then Stephanie Reed is our 4th member, and she's actually someone special to me. She's one of my PhD students. Okay, she just graduated, and she's now currently systems engineer in Advanced Bionics, where they work on artificial cochlear implants, and she's only utilizing half of her engineering skills. I always joke that she's not playing with stem cells, she's not doing tissue engineering anymore, but eventually she might. She earned her bachelor degree from MIT in mechanical engineer, where she won the MIT Charter Award for Excellence in Bioengineering, working with some of the premier experts in the field. Paul Masudera, who co-wrote the textbook in molecular cell biology, Doug Laufenberger, chairman of MIT Bioengineering. So she's worked with some big shots until she came to me. And so downhill from there. At UCLA, she got the MS and PhD in bioengineering, where she worked on materials that you can implant, that you can work in the 3D printing technology. So you know, 3D printing is great, but most of the things you print, you won't come near a human person. And what she's working on is not just how to work with these materials, but to make them with very special architecture, and she's going to tell us something about that. At UCLA, she won the John Benn Scholarship and a bunch of other awards, and she's truly one of the outstanding PhD students from bioengineering department. Okay, so now I'm going to go ahead and go into 5 minutes of presentation on 3D printing, and I won't have time to really talk about what it is, but let me just give you a flavor, okay? If you were going to a dentist and they were going to make you a computer-aided crown, something that's made on a computer, it would be something that looks like on the right, on your left side, where there's a drill that will basically take a block of material and grind it down to something that shapes like a crown. Okay? We call that subtractive manufacturing, where you start with a big piece of stuff and you make it very, very small and custom fitted. It's a terrible waste of material, right? And then the other technology, the whole class of technology called additive manufacturing, is where we build something up layer by layer. So the slide on the right shows you what happens if we want to build a crown today. We actually will build that layer by layer, one layer at a time. Every layer will look different than the layer next to it, okay? And in 3D printing, there are probably 5 major ways that these layers are made. Some layers are made one layer entirely at a time. So imagine a flashlight that flashes that whole layer and we get that one shape. Some technologies make the layer one line at a time. Okay, so something moves around and makes the layer one line at a time. And then some technologies make it one little dot at a time to form a line, and then goes back and form a second line. So dot by dot, they would make these 3-dimensional parts. Okay. And you know, I did my PhD in 3D printing long time ago, about over 20 years ago. And so when I went there, I thought, oh man, this is what I want to do because no one's done this. I'm the first in the world to do this, right? And then, of course, if you read enough, you realize you're not the first. So it turns out that a French artist, Francois William, did this thing called 3D photo sculptures, where he would take 24 cameras okay? Connect them with one single cable, set the cameras 15 degrees apart, and those of you who are quick in math will know that 24 times 15 equals 360. So he forms a circle. He takes each one of those negatives and he traces it on a piece of wood, 15 degrees apart per trace. And in doing this layer by layer, he basically could create this sculpture that you see on the right, okay, where he traces it, and connecting the trace is a pantograph drill. So he's drilling the wood layer by layer, and then he glues it all together. And if you were to go to his studio, he will do this for you for $80 for a full body scan, okay, $40 per head, and it'll take about 2 days. That's a good deal, right? Well, it's a good deal back in 1859. Today, it will cost you $500 easily, okay? So, and even back then, what's amazing, if someone translated the text for me, photo sculpture was part of the modern world back in 1859. So far, it represented the merging of art and technology, okay? And today, there is no better example of that as some of what you'll see later. Now, this picture on the left shows you the studio that Francois used. This is a big rotundum where he lines up his 24 cameras, and rent back then was probably $1 a foot, right? Today, on the right, just came out on the 3D printing show, is this whole body scanner where that set of cameras spins around you. So they don't need 24 cameras set 15 degrees apart. This guy will spin around you and give you a 3D picture in full color, okay, in less than a minute. And then you can send that file out to 3D printing. That's incredible, okay? And the reason that it took 20 years between my PhD to now, the explosion of 3D printing, is because of the convergence of core technologies. If you think about how things have progressed between the early 90s to today, the biggest change is computers. Your cell phone today, it's got 10 times more computational power than the computer I used to build my machine. The software I used back then came in, to write the program, came in 46 floppy disks. You guys know what that is? You guys know what that is, all right? Stephanie never heard of floppy disks. 46 floppy disks. It'll take me a day just to load it in because the bus was so small, right? And then after it puts in the computer, it pretty much takes up half my hard drive. Today, your phone can do much more than that. Your desktop computer comes now preloaded with this 3D builder software from Microsoft. You can actually design 3D models on that. Medical imaging is ubiquitous. When a patient calls me from London and they want me to evaluate whether they are a candidate for a certain head and neck procedure, I could access their 3D medical file in real time and look at it and do everything we need and do real-time and computer analysis. The 3D scanners now, handheld, are ultra accurate. You can scan somebody and get about within about 0.5 millimeter of error, and it's only dirt cheap. Your phone can do 3D scanning. It's not perfect, but it's actually pretty good, all right? But the most important driver is that 20 years ago, all the patents were filed. 20 years later, they all expired. All the companies now are living on old patents, and that's why there's an explosion. Everyone can make the same machine without worrying about infringing, okay? And so the same machines are being built using really similar material, just different colors. It's an amazing story of how technology and legal and society really converge to create this thing. And then finally, because of this explosion of technology, we now have many materials. Back then, 20 years ago, there would be maybe 10 materials, and 9 of them you have to make yourself. Okay? Now, you can pretty much buy materials, and you can buy them as commodity prices, really cheap. okay? So what that means is that 3D printing can benefit those that are really tech savvy, and whether you are a PC user or a Mac user, I'll let you decide which one's the geek and which one's the nerd, okay? Two, whether you are just a super creative. 3D printing now allow you to create from scratch. And some examples include making parts that doesn't exist, okay? In the old days, we would just make something that looks like a jet engine. Then pretty soon we made a casting mold, actually out in California, where we would 3D print a casting mold that you would cast hot molten metal into to make these machine parts. Now, we make the metal part directly from 3D printing. There's no mold anymore, okay? In medical devices, we are certainly taking a whole new approach to personalized healthcare. This is a model of a mandible of a lady who actually had a lower jaw completely removed, and this is made and printed in titanium and implanted so that she can eat again. Of course, that jaw has no teeth, right? So some dentists went in and connected that jaw to a set of custom-made teeth for them. The teeth now are 3D printed. We can actually make one tooth, a bridge, a whole arch. We can make dentures. We can make artificial noses, artificial eyes, artificial ears. That is what we call advanced prosthodontics. We are actually restoring not just the teeth, but also the facial structures. The bottom left figure shows a custom-made sleeve that's going to hold this airway open for an infant. So this infant was born with a genetic disorder where that tissue is not strong enough, so the airway collapses. By connecting that airway to this little sleeve that is made on a 3D printer, out of a material that will slowly dissolve away. So you don't have to go back and remove this. It's basically a life-changing solution for people who only need one, and no one else needs that, okay? And of course, prosthetic leg, and you heard a lot of stories about artificial organs, artificial tissues. I'll show you some stuff that we did back in the old days where we made a skull mold, and we filled that mold out of a biomaterial that you could actually implant into humans for bone regeneration. So those are just coming, and of course, as Yulia will show you later today, 3D printing has changed the way we think about fashion, and she will actually show you what it takes to make one of these beautiful dresses, okay? And decorations that you really couldn't make any other way because it would take you so long to do this by hand. Shoes and hats and all kinds of amazing design. So this is for the super creative, all right? The medical stuff, the engineering stuff, that's for the geeks. And of course, 3D printing should touch your soul too, right? This is a picture of a Stradivarius printed in a material that actually gives it the acoustic property to sound like music. And then most recently in 3D printing show, on the bottom right is this new violin that's designed and actually functional, made by 3D printing. Electric guitars and saxophones, you name it, they printed it, all right? And so this is really an amazing explosion back in the old days when we thought all we cared about was jet engine parts, to now houses. There are 3D printing machines that can actually build houses from the very large down to the very tiny. So the figure on the bottom right is a nano manufactured bull. This is a model of a bull, okay? So I think Wall Street people would like that. How small is that bull? If you look at the upper left figure, you see that human hair? A human hair is about 60 to 70 microns. That bull, next to the hair is that little black dot, okay? That's how small they can make these things now. Now, this is a model. okay? Professor Lee is going to tell you what we can do if we can manufacture at the nanoscale. So, this is really an amazing opportunity for me to learn about what these experts have been working on. And without further ado, I'm going to just now invite Yulia to come to the podium and give us a 5-minute talk on her work. Okay?
Hello, everyone. Thank you so much for having me tonight. I'm really happy to be invited to give you an introduction about my work. So my name is Julia Körner, and thank you so much for the really great introduction. It's difficult to jump in, because I think you gave such a broad insight about what 3D printing is, and I find all of the topics you talked about super interesting. And it reminds me on a recent publication in December last year, there was a double page within National Geographic of one of the dresses, what I have designed with Iris van Herpen. And it was next to bioengineered ear and like a suit for NASA. So it was really within all the sciences next to it printed, and it was super exciting to be part of that article. So to give you a little bit about background about myself, I'm trained as an architect. I graduated from the University of Applied Arts in Vienna in Austria, and I did another Master of Science at the Architectural Association in London in Emergent Technologies and Design. And what you can see here is one of my images from my thesis at the Angewandte, where I looked into a biomechatronic research center and how a building could sort of look like in the future, thinking forward 10 years, maybe even more. Next. So here, just show a couple of images. I'm super inspired by nature and by biology and how that could influence not only material performance and structural performance, but also aesthetically inspire my work. Next. So I work a lot with 3D scanning, and the recent picture you saw was a 3D scan of an ostrich bone and inspired me for the image before. Anyway, so I also worked as an industrial designer in London with Ross Lovegrove, where we realized product designs which were not 3D printed, but I want to give you a little bit of an insight of the work I have been doing in architecture and industrial design and how these different disciplines merge together due to the work I do in 3D, and which allows me to bridge disciplines in a way. Next. So I designed with Ross Lovegrove light designs for Artemida, which you can buy in Artemida stores, and it was really exciting to be part of that designs because they both look into advancements in manufacturing, whether it's like injection molding or vacuum forming, and how to integrate these rather emergent technologies into real product design, and to work on the cutting edge of designing these products in 3D parametrically, so that you have a certain digital level which you, with other ways of production, you wouldn't really be able to realize. Next. So I want to talk also a little bit about my work at UCLA. This is an image from the Howard Hughes hangar down in Playa Vista. Our location is next to the YouTube spaces, and I teach there the MAC2 program in architecture together with Greg Lynn, and we are teaching the MAC2 students in advanced architectural design. And we work together with industry partners such as Boeing, Cirque du Soleil, and we have really amazing lecture series. So if you're interested, you should come down. It's a fairly new campus. We are there since 2 years, and it's specifically for our MAC2 students. Next. So we work with large robots, and we put with the students models onto the robots, and we move them around and research how robotic technology can be included in the design process. Next. Next. So what you can see here are a couple of designs from the students' work where they worked on future factories ideas for Boeing. That was last year. Next. This is an image from this year from a student's project for Cirque du Soleil and rethinking how a movement in building structures could change the way we think about static buildings. Next. 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 So beyond that, I also teach technology seminars where I closely look with the students as of how they can work with new technology such as 3D scanning. And as Dr. Wu before mentioned, you can 3D scan now already on your phone. So I had the students 3D scan natural systems with their iPhones with open source software, later on analyzing the geometry in 3D and 3D printing the geometry, learning from the geometrical structures, what they found in these three-dimensional objects, and scaling them up to make larger pieces of panels with composite material fabrication. Next. So what you can see here, working with the student, filming and 3D scanning a coral. And on the right side, you see a close-up shot. Next. Another model, what the students put onto the robots, and they moved it around in order to see spatial configurations and how movement would be integrated in architectural space. Of course, in a model scale. Next. 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 So beyond that, to explain you a little bit about the 3D printing, what I'm originally interested in architecture, 3D printing is mainly used for producing mock-up models. Of course, we saw there are some people who are 3D printing real houses already, but in what we learned back then when I was a student, we really used 3D printing to output our ideas from the computer. So what you can see here, and if you go to the next slide, I looked into cellular complex systems from sponges or natural geometries and transferred them with the help of the computer into three-dimensional structures. Next. So here you can see a diagram of how the algorithm was developed to produce such a cellular complex structure. Next. And structural analysis, how to improve the complexity and the performance of the structure. Next. And then real-scale mock-ups for facade systems in a metal prototype, which won an award at the TechSfab competition and was exhibited at the conference in Toronto 2 years ago. Next. And we also did plasma cutting with robotics. And next. And then we had an exhibition at the A+D Museum opposite of the LACMA last year, where we showcased 36 student projects. It was a design for an exhibition space where we exhibited students' work, and we were asked to design the display wall for this. Next. So what you can see is I'm really interested in how to work from the micro scale and bring it up to a larger scale with architectural methodologies of design. Next. So what you can see here is the machines which I use to work with Materialize to produce my fashion designs. And now I come to the last chapter. Next. I work a lot with Iris van Herpen. She's a Dutch fashion designer from the Netherlands, and she's the youngest member of Haute Couture. And we designed this dress in 2012 for her Haute Couture show in Paris. It's made in 2 pieces, and it's made with a mammoth stereolithography machine. So the printing process for this design was about, only a single print of the front part took 5 days. So speaking about time, the moment you increase the size of the 3D printing, the longer it takes, and of course the costs also get higher. But there are really machines where you can already print in full scale garments and dresses. Next. This is a close-up of the detail level of what you can get of this very honey-colored structure. Next. And this was a breakthrough in fashion, 2013. It was for the Voltage Haute Couture show and was the first ever printed dress in a flexible material. When we worked on this dress with Materialize, Materialize is the 3D printing company we work with in Belgium. there was no real name for the material yet. So they really came and said, well, here's a new material, it's flexible, experiment with it. So that was an extremely exciting moment. Next. And the most recent one was the biopiracy dress, which was actually for the first ready-to-wear show. And it was also printed with the new material TPU, which is a flexible material. And it actually was printed in multiple parts because that particular printer doesn't allow yet to print in full scale. So the flexible material is still not yet there where you can print full-scale pieces. Next. And finally, I would like to show you a couple of pieces of my own collection, which I launched in March this year. So these are really images which haven't been published anywhere yet. It's a collection of 3 jackets, if you go to the next. And the intricacy of the material is highly dense, and when it's flexible, so you can imagine it's like stretchable material, and from multiple different directions you can see through, it's disguising the body and works really in a great way. It's inspired by a mushroom surface, and that's why it's called Humanium jacket. And I'm currently working on producing photographs with real models, and so soon you will see in the news a lot of pictures with models really wearing this. So my idea is really that I want to get this off from the catwalk, off from museums, and seeing it less as a sculpture, but actually as wearables. And I want that people start being able to buy these things and actually wear them in events and public events, or like even music events. Next. So here you can see a detailed close-up. Next. And this is the other jacket, which actually has a translation from hard to soft material. And so different parts are printed in a hard material, where you don't need so much movement, and other parts are printed in a more flexible material. So it really works with the body, and you can customize it for each individual user. So you can 3D scan any person's body, and then you can customize for whoever wants it specifically. And this was done with a company in the United States. They are named Stratasys. And it was launched in Minneapolis in March. And finally, I want to show you a video where you can see a little bit the process of how one of these dresses was made, and where you can see how the production was done. Thank you.
Yeah, thank you. So looks like the previous two speakers already talked about everything I like to say.
So we're
So I'm under
Show
pressure.
Studio,
So
we're
obviously
embarking
that
on a very
fabulous
exciting,
talk
very ambitious
and the excellent
project
vision
with
there.
Iris van Herpen,
So,
who we're delighted to have with us. So thank you, Iris, for joining us.
give me 1 second.
Thank you for inviting.
Yeah, I'm a manufacturing engineer, as you already saw the introduction. So I'm blue collar guy, right? So I need to go dirty. So what I will talk about is more like how to make, manufacturing applications. So we know that manufacturing is use manual, right? Use hand to make something. And in the 1,000 years, we have raw material, right? We chop the material off to make shapes. Just like in kitchen, you chop some kind of food, material off to get some shapes. Or we use mold to make cupcakes, something to mold, right? So net shape, that kind of manufacturing process. Traditional, just two processes serving us well, right, in 1,000 years. But obviously, they have limitations, especially when we're dealing with very difficult materials and with very complex geometries. And they use the machining method, removal, or use forging or molding method can be very expensive. Like either very difficult to automate that, CNC machines or that, drilling machines, or very difficult to make the mold. Right? Cupcake is easy, but to make very complex geometry for turbines, right? So it's very difficult to make the mold. So obviously, they have some need how to make that fast, dealing with complex geometries. That was the original motivation for manufacturing engineer to develop so-called additive manufacturing. Today, we more call 3D printing. So the 3D printing really that at the start, right, from the academic point of view, from manufacturing point of view, we call rapid prototyping. Like we like to make prototypes really quick, right, to test the products. So that really started from computer-aided design model. Right? That's why this is coupling very closely with computer technology. Without computers, it's all the layered manufacturing, so-called 3D printing technology, will just manually make something, will very slow. That's why there's no motivation from manufacturing point of view to make it happen. Until 1980s, computers became viable. People realized, okay, I can use computer to make layers, to make planning well. So that we can use computer to design any shapes we want. And then we can slice them to any layers we want. So with just two technology together, we can get any complex geometry we want. So this was that motivation for manufacturing engineer to get in the field in 1980s. And obviously that with the physical machine, so-called 3D printing machine, we deposit any shapes layer by layer, right? So you something about me, I'm standing here. So you can imagine just cut to slice layers, right? You just put me up. So today we say, hey, just physical model, but the people even dream about in future a day, although I don't like that, day to happen, so they like to print the human beings in one shot. Right? So it's possible. I'm not trying to scare us, but biologically it might be possible. We can really cell by cell print us up, right? So just duplicate us. I don't know that will engineering possible, but the vision-wise, right, that could be possible. So anyway, by layer deposition, so so we can realize that easy planning for any three-dimensional shapes, right? So any shapes we can deal with two dimensionals. Right? Because human can deal with 2D very well. We draw on the board very well, 2D. Right? So with 2D stuck together, any 3D, we solve the problem. Right? So very easy. And also in each layer, we can put a different material there. Right? So we can think about birthday cake, different geometries there. One layer chocolate, another ice cream. We can put any material in. Right? Just what type of 3D printing of chocolate, 3D printing ice cream is happening today. Right? We like to do that. And the day you're about to buy that, okay? So with the kind of geometry, with the kind of technology, we have very fast turnaround, that kind of, technology. That means I have an idea today, I will just design computer model, send it to machine, tomorrow I see the model. Traditional manufacturing engineers, when we like to design a new shoes, will take us maybe 1 year or 2 years from design to final testing to the market. Right? Today, just maybe 1 week or 2 weeks, we will just send it to market to test, right, the customer response. So that the fast is the key competitive edge we have as a manufacturing engineer to make it fast, make it complex. So of course, we have weakness here. So we still try to solve the problem. It's the accuracy, because dealing with layer thickness. Right? You can think about, we solve the complex problem, but we also have the problem, we need to stack layer by layer very slowly. Of course, you can say, how about I go fast? Of course, right now we go to as fast as possible. Another way people say, how about go thickness a little bit thicker? So that would be a problem. You think about me, right? You like to put me up, sculpture. So if you talk about 3 layers, that would be a problem. I only became a very weird shape. If you talk about maybe 3,000 layers, you slice me to 3,000 layers, and you are similar like me. You can see me, right? So they talk about layer thickness. That still is one thing related to accuracy. It's a dilemma here. We like to go quick. We need like thickness a little bit thicker. But if we go too quick, the surface will have a problem. Right? So we still try to solve this problem today. Right? So no matter what we do, so you talk about speed and accuracy. These two things needed to solve. Right? So it's compromise between the two. And here just show the early days from the university point of view, like professors are weird. Right? We call the 3D printing as a solid freeform fabrication. That means we start creating 3D solid model in computer, and then to fabricate any shape you want, right? Any form you want. So they call solid freeform fabrication. That's universities still call that way. When we teach in class, we still teach it that way. But general public, obviously the name even better. 3D printing, right? We know the printing very well. So, and the 3D printing obviously dealing with traditional manufacturing technology, and then with computer technology, also with all the electronics, lasers, and the motion controls, right, in the last 20 or 30 years, that became very competitive technology when we compare to traditional manufacturing. So here that I think Dr. Wu already mentioned a lot of beautiful stuff there. I just go to the manufacturing point of view, right? So basically we can create any shapes you want. That's pretty much true. And the process is automated. You do not need any human intervention during the process. You send your computer model in, you just set the parameters, they just build it for you, right? So this became very easy. You can see in reality, really we build parts like this, layer by layer startup. And the benefits, early days, obviously, to compete with the traditional manufacturing is very difficult. Because, like 20 or 30 years ago, people say, we don't need that 3D printing. We do not need it because the traditional manufacturing can do well. We produce product day in and day out, right, in the reasonable cost. Obviously, that you have some kind of niche application there. But obviously, the first application for design, right? So to show the models to the market much faster than traditional manufacturing. So this one that, visualization, verification, iteration, and design optimization for any products, that get some products, get some competitive edges into the market. And the communication tools for simultaneous engineering, especially talk about global engineering, right? You talk about different countries, talk about some product design. Of course, today we have a lot, internet-based, like a tool. But no matter which tool you have, physical tool still the most direct, most the intuitive way for us to communicate, right? You can imagine your manager or my manager, so in the company, right? Normally, a lot of managers might be not in technical the way, right? So if you have physical model to communicate your technical, the content will be much more effective. And also marketing studies, right? To have that a few or a couple hundreds products like cell phones, right, to the market early on without much cost. That would be really fantastic. Because in traditional sense, if we would like to test a cell phone, the model, we need to spend a lot of money, more than 1 or 2 years, to even make that sample product. Because use traditional manufacturing, you need to develop tooling, right? First design, tooling, and then produce them and go to the market. By use 3D printing, you save all the money. You just print out, send it to market, let the customer to test them first, right, to see which one they like. And especially from manufacturing point of view, the metal tooling, metal prototypes is one of the niche application, right, really gain a lot of momentum these days, right? So because metals, right, it's the way when we make a lot of new products, like injection molding. I don't know if you know any shoes or chairs or a lot of computer, their frame, that kind of cover. It's all made by massive production, use injection molding, right? So that kind of method that produce a lot of product in 1 hour and in very low cost. That's why manufacturing right? It's valuable because it produces very low cost product, so we can buy. So here, obviously, people were debating, hey, I have 3D printing now, so I don't need your traditional manufacturing. Or some die-hard traditional manufacturing guys will say, I don't need a 3D printing. I can do whatever you tell me to do, right? So obviously, the two are in competing their position. But in reality, really not competing against each other. It's complementary. Because what happens, for example, right, people use the injection molding. This is the massive manufacturing tool to produce a lot of, shoes or chairs or computer that, like discs, anything, right? I mean, computer that cover. So this one, generally speaking, the cost, when you produce more than 10,000 or 100,000 or 1 million or 10 million parts, will go cheaper and cheaper, right? So the parts of $1, the price per number, injection molding normally, really successful when they produce larger numbers. 3D printing, however, can be very successful, just fit your niche need, only for you, right? Or just one of the kind product. So because their price for the number, no matter which number you talk about, day in and day out, the same price, okay, same price. So basically, they could have a trade-off or compromise here. You could use rapid prototyping or 3D printing to produce injection molding tool, right? Can reduce the cost. Right? Or you can use injection molding, the method, to produce lower cost 3D printing machines or systems. So they are helping each other. Actually, that's the way to go. And here are some tools I produced when I was a student in 1990s. So at that time, it's at the peak, golden age of 3D printing. Right? Today, it's more like, okay, post-golden. It's platinum test, the age. So at that time, it's because every year, every month, new process and the new scientific stuff come out to the 3D printing field all the time. And some of the fancy tool I talk about, very complicated injection metal tool. And then you have assembly of this kind of different polymer parts, very complex geometries. Like recently, you also heard the news maybe talk about 3D printing cars. Right? They are doing that right now in Oak Ridge National Laboratory. Right? So people are trying to print the cars from the design. So I think maybe in 5 or 10 years later, we don't need to buy the car like other guys. You can design your own car and then just print out in the market. So that will be good. Hopefully it will be cheaper enough for us. Next one. Yeah, here Dr. Wu already mentioned that there are a lot of micro, nano scale components. Because you go to micro, nano, it's very difficult for manufacturing engineer to use hands to do it. You remember I talked about manufacturing. Use the hand to do something. When you go to micro, nano, our hands doesn't work anymore, right? Our hands are too big. So obviously they're fascinating that work toward this end. Use 3D printing, use micro, nano layers to print out micro, nano mechanical systems, even like this cast, like 1 millimeter long, right? And also stand, right? This kind of geometries. So one thing we always show, even go to micro nano scale, we can go to any geometries you want. And that's the key, that competitiveness against traditional manufacturing. So here, the medical use, I think Dr. Wu and the next speaker will mention that. I'll just go quick. I just talk about medical use. And talk about medical implants, right? We use the titanium or use some other material to build implants. Right now, it's already in the market. Yeah, using that for the patients. Next one. And here also talk about scaffold for micro 3D printing. Dr. Wu already mentioned basically this, micro scaffold can put the human cells or some kind of biological material into it to let them grow and to the shape and then dissolve this material away. Then we can get, regenerate the kind of tissues or biological organs. And that's happening now. And here, obviously, that we not only can produce the scaffold, the mechanical structures, you can also print the cells and the structure together in one shot. Right? Talk about integrate 3D printing of biological systems. And that also happened now. So that's all I have to offer. So thank you.
Hi, I'm Stephanie Reed, and as Dr. Wu mentioned, I was a PhD student in his lab. I had the privilege of working with him in the field of tissue engineering, and I got to use the 3D printers that he had available for us. We worked with putting stem cells on precisely controlled scaffolds that had very small and precise architecture, and the idea was that you could make these implants that you could deliver and put into the human body that would regenerate different tissues. Today, I'm not going to talk too much about that work. I'm mostly going to be focusing on a little bit more of an industry perspective and FDA-approved medical devices that have been made by 3D printing technology. As Dr. Wu mentioned, there are a few different types of 3D printers. There's powder-based 3D printing. There's a laser that kind of fuses together different powder particles as a method of 3D printing. There's the hot glue gun approach, as Dr. Wu says, a fused deposition modeling, where you can print out different plastics in an extrusion method. And there's also a photopolymerizable method, where, again, you can use a laser to kind of meld together a liquid polymer. And all of these different printing options have benefits, and they all have drawbacks. And so it really matters about what your application is, which type of 3D printing you would want to choose. So I won't go into the detail there, but I just want to make it available that there's many different types of materials and ways to 3D print. So reasons why 3D printing would be useful and reasons why they might not be useful in a medical device setting. The pro is that you can buy a 3D printer for $1,000 to $5,000. And you can get it very quickly, so it's a short lead time to have any device. The drawback is that printing every single part can take many hours. And as we just heard, if you have to print tens of thousands, hundreds of thousands of parts, like my company does, it's not necessarily time efficient to spend that long. And so we do a more traditional manufacturing approach, where maybe you pay $50,000 up front for your traditional tooling, but then you can make all your parts, like gangbusters, and just produce them very quickly. Another big advantage of 3D printing is you can have patient specificity. So you can use a CT scan or an MRI of any patient and create a part that's custom fit to that patient's anatomy. The drawback in a medical device setting could be, because of this specificity, you can't really scale up. Every person needs their own prostheses or implant. You can't really mass produce these, so that might be a bit of a challenge. Also, you can create more complex geometries, more difficult undercuts, interlocking materials, and you don't lose or waste as much material in the process. But a drawback of this is that if you use powder-based 3D printing, you have to excavate your part out of this powder bed, somehow blow out all the loose particles, or if you're using a different type of 3D printing, you have to use a support material, because you can't print on air. You have to have some kind of support, then you have to use solvents to dissolve that support material away. One of the biggest and I think most driving factors for 3D printing in medical devices is that you can make very quickly and very inexpensively design adjustments, such as the Invisalign, the alternative to braces, and you can accommodate growth of pediatric patients. One thing you have to consider is whether this material is biocompatible, and 3D printing doesn't let you print with any material that you want yet, but that is definitely improving. And there's still questions about the tolerances you can get with this type of 3D printing and the resolutions. So all that being said, I'd like to focus obviously on the pros of 3D printing and how it's been used in currently FDA-approved devices. So a lot of surgeons have been using 3D printed organs like this liver or this bone as a way of planning for surgery. So they can have foresight, know what they're doing, not make mistakes, not cut away excess tissue, and it improves the surgical procedure. Another way that 3D printing is used is for prosthetics. Actually, this is an instance where a father bought a MakerBot for about $1,000 and 3D printed a mechanical hand for his son who suffered from amniotic band syndrome and lost his fingers. So the parts of this hand were actually only $10, and he printed them all themselves. And as you can see, now his child can draw, catch a ball, ride a bike, do all sorts of things that he couldn't have done before. So obviously this is a very beneficial technology. And then finally, and what I'll give a few examples on following this, is the use of 3D printing in tissue engineering. And so you can see you can take three-dimensional models, such as for breast reconstruction, and 3D print some kind of implant that would be patient-specific. You can also use 3D printed molds to create a vascular system to help create more vascularized implants so they have a better chance of surviving and receiving blood supply. So this bit of research here is not yet on the market, but I think it's a good example of 3D printing. Here they took a specific type of plastic or polymer, and they were able to create this artificial aorta. And by using different materials for different parts of the aorta, they were able to capture the mechanical properties of a native aorta and tissue. So this work was done a couple of years ago, and you can see they can do a variety of sizes for different sizes of patients and a variety of mechanical properties. As Dr. Wu mentioned before, a couple of years ago, a woman had her entire jaw replaced with a 3D printed titanium mandible implant. And as Dr. Wu mentioned, the teeth would be fitted here, and this is a bit of the implant procedure, hopefully not too gory. But you can understand how this would be a really beneficial and life-saving technology. Further, there's another company that has recently emerged in the market called Oxford Performance Materials. And they have their own specific polymer blend, PEKK, which is supposed to be a bone-like osteoinductive material to help the bone grow into this implant. So these implants are permanent. They're not made to biodegrade. They're made to be there permanently, similar to a knee replacement or something like that. So here a man had 75% of his skull actually replaced with this 3D printed material. Another company called Arcam makes 3D printed knee replacement materials. You can see the acetabular cup on the top. Again, skull implants, different features to replace potentially voids due to trauma. And Stryker, which you guys may have heard of, it's a pretty popular medical device company. They have also released a new knee replacement system where the tibial plate portion here is 3D printed titanium. That's also been coated with a special chemical to help bone grow in and fix better to the bone so you don't have loosening over time. And they're able to make very smooth regions and very porous regions with their 3D printer. So you can get a variety of textures, which is important for helping the bone grow in. And finally, this is an example that Dr. Wu also mentioned, where a young infant was born with this disease where the airway in the lungs was collapsed. So here you can see this portion. They infused a dye into the airway. You can see it's collapsed. It's been blocked off. No air can go in and out. And this little girl was living on a ventilator until they were able to receive emergency FDA clearance for this 3D printed stent, which they basically put around the airway to help open it up. And this stent is resorbable. So the idea is the cells will infiltrate and eventually degrade this material while simultaneously bolstering and building up this airway that was previously collapsed. So within 3 weeks, this child was able to be off ventilation. And a year later, you can see that this once previously collapsed airway is now open and fully functioning. This same company, that Tissue Regeneration Systems, they work with University of Michigan. They also have another product, which is a bone void filler that fills neurosurgical burr holes. This is also another bioresorbable material. And so finally, these are just a few of the things that all of our speakers have been hitting on. Where's the future of 3D printing going? Particularly for tissue engineering, what are the barriers? What are the benefits? And so as people have talked about, you can encapsulate cells in the 3D printed material as you're extruding it. There's things to consider like biocompatibility, whether or not the cells survive, if you could get blood supply into these implants, the resolution, the cost of the printer. So all of these things are improving at a very rapid rate, so it's a really exciting time. And then lastly, I just wanted to comment on whether or not the question of whether or not 3D printers will actually make it into everyone's homes. And this reminded me of some previous historical mispredictions, I would say, where the technology was in advance of the applications. And I think while you could think about, oh, I can 3D print a spoon at home or 3D print toys for my children, I think the applications are going to become more and more obvious as time moves on. And this technology will be able to really work with people's creativity. Thank you very much.
Thank you, Stephanie. Let's give a round of applause for all the speakers again. So now it's your turn. I'm sure that you've now heard enough and you're ready to have some burning questions answered by some of the world's experts in the field. So there are microphones on the side. So please come up to the side so that everybody can hear your questions and direct them to one of the panelists.
I think this is all completely fascinating. And I noticed that you said that the time to print is fairly long. I don't know what that means. If you were making, I don't know, a jaw, let's say, would it take weeks, days, hours? How fast does it work?
Professor Lee?
Yeah, the speed of that printing depends on different materials. For the jaw, like biomedical stuff, maybe only take a few hours, really. The key thing really to make it biologically that, viable, right? The shape is no problem. We can go very quick. Even like metal, the prototypes we show might be, generally speaking, you could build 1 cubic inch per hour easily. So that kind of speed, I would say. So for the biomedical speed is not a problem. The problem is really biologically that, functionality is the key.
Yes, thank you again, everybody, for a wonderful presentation. My question is, are there any long-term studies to show the effect of the resorbed material on the host immune system?
You want to take that one, Stephanie?
Sure, I'll take that.
This is your post-PhD exam.
Yes. So the remnants of the material from a 3D printed polymer stent, for example, are no different from any other type of traditional scaffold that you would implant. And every different specific material, whether it's a natural polymer or a synthetic polymer, they all have a different immune response and a different degradation timeline. And so different tissues in the body may better lend themselves to different types of materials. And so that's something that tissue engineers are definitely focused on, is making sure that the implanted material is safe over the course of many years.
I would add that FDA pretty much will only approve materials that have a long track record of being implanted in humans. So the little stent for the airway, all the things that degrade are already using the sutures that we've been using for decades. But that doesn't mean they're safe, all right? All materials will induce some inflammatory foreign body response. And some people have no problem with them, some people have big problems. So, it's a very personalized response. But in terms of material selection, only those that have long history of human implantation can be used.
Hi, I'll add my thanks to bringing this particular sequence of speakers together. It's sort of like building something out of a 3D printer. Step by step we understand what 3D printing is all about. I come from the field of public policy, and I can't believe that the regulators aren't going to want to get their hands onto this process somehow. You mentioned you had to get FDA clearance for some of the devices. Where do you think are the opportunities for policymakers to get their hands on this process in the future?
Maybe this is a question for Professor Lee and also Stephanie because of the interaction with industry.
Yeah, I think that, obviously when the 3D printing became more and more popular in the industry and also in the consumer market, I think the policymaker will have a huge role there. For example, right now 3D printing product, they have quite a good success, but it cannot be still compared to traditional sun kind of products, they have almost 99.99% they can successful rate, right, or reliability. So basically, standardization, that one, I think, from the policy point of view, need to ensure our product from different machines produce same quality and same reliability. So this is going on right now, right, from technical management point of view. From the public safety and also public, the response to the new product point of view, they could also have a lot, I think a policy, to make sure our product, meet all the requirements like FDA or even even talk about the material use or so-called sustainability. So all kinds of this kind of aspects will be big. So obviously we can see when the revenue or when the sales of 3D printing product right now is about not so huge, I would say about $10 billion now, right? It's big enough. I think the public policy should get in to really have some good look at this industry. Yeah. Thank you.
I'll add a little bit. So I actually have been in front of the FDA to talk about some of these opportunities, and there is a vast resistance to really think about devices that are made one at a time, one patient at a time, and that they really don't know how to regulate it. As Professor Lee said, if you were to make 1,000 widgets and you take out 10 of them and you break these widgets, you break all 10 of them and you get a certain average value, you will know how, you can predict how the other 990 will perform. With 3D printing, you make one stent, and that's the one stent. There is no breaking 10 of these things, right? That's the whole idea. So how do you do this? If you actually now are not just including materials, but now patient-specific stem cells, right? How many cells on this side of the implant? How many of this other cell in this other side of the implant? How do you know that 990 out of 1,000 times this will work when you're only making one of them? So the opportunity, I think, is really in doing some very sophisticated statistical analysis and predictive modeling that requires more sophistication than what currently FDA is capable of doing. That is, how do you predict success or failure based on very limited sample size, as opposed to making 1,000 of these things?
Question here. Has there been any work on developing a primitive living organism?
So not without assisted devices. So if it was just printed and left alone, it wouldn't be living. But if it's printed, put into a bath of nutrients, put into a environmental controlled chamber with the right CO2, with the right gases and the right condition, then those cells can live and they can multiply and they can differentiate into the right cell types. People have made artificial blood vessels based on this concept, artificial bone. So there have been examples of this, but properly manipulated.
Well, it's a very exciting future.
The future is now.
Exactly.
In traditional manufacturing, especially metals, the grain structure of the metals is important for strength and stresses. So I'm just curious, in 3D printing where metals are concerned, can you control those structures in the same way to control strength and elasticity and that kind of thing for critical part manufacturing?
Yes, theoretically, that's one of the early dreams of 3D printing, right? So people say we can use layer manufacturing really to manipulate that the microstructure and the strengths in each layer. We can design, right, to the so-called the material gradient or microstructure in any way we want. This is the dream. Today, we're still working on it. Actually, one of my research topics still try to control the microstructure in each layer. So obviously, it's a difficult task because right now, we talk about dealing with high temperature metals. Each layer, we talk about you almost like in some way micro casting, right? Each layer micro casting. You hit the metal again, cool down, hit up again, cool down again. So it's always a struggle between the perfect microstructure and the realistic manufacturing process. But I would say that we are making good progress, so it's going in that good direction.
Yes, this is a perfect segue. Some years ago, in a conversation with the chairman of the Federal Aviation Authority, the issue of false rivets, which were not made of very strong material, but stamped as if they were made of very strong material, entered the product stream and posed an enormous danger to the manufacture of aircraft and the safety of the general public. And it occurred to us in the conversation that there had to be a means for authentication of the material itself, which was used to cast or make the particular rivets. And that leads me to the question as to how would one authenticate the casting material, the quality of the material itself? Has there been any general thought about the nature of authentication of the substance? With the proliferation of home printers, one can only imagine the proliferation of forgeries of all sorts. Yeah? Thank you.
Well, I know at the company that I work at, there are a lot of requirements to prove that the materials you're working with are the materials that you say you're working with. The question of whether or not something you buy off Amazon is really the grade of metal that you're looking for, that's a tougher one. I'm not sure how to address that one.
Yeah, I think that's a really important and a tough question, really. So because, when they, 3D printing go to our home, day in and day out, the kids really don't know anything, right? They just play with the materials. It could be dangerous too, right? So how to control the material that, to be, safe, and also make even structure to be safe. I think this one we can only say with our, electronics, computer technology, we can hope the 3D printing machine will become smarter, or even can link to the internet, can have some kind of central control system to monitor that whole process there. If they sense something, they should shut down the machine. So at least just like computer have that, protection there, wireless software that tell you, hey, wireless is coming. So something like that will help, but I don't know how to completely get rid of that, potential problem, right? So that could be by more education to the users, and also might be, like we say, more like intelligence into the machine itself. So.
Yeah, I don't think you can count on federal regulators on that one. But there are user groups. You look on the internet, there are 3D printer user groups with hundreds of thousands of pictures from things that people made. And they have little chat rooms on different materials that work better on some machines. And maybe you start, if you search, maybe you'll find that some materials are irritating to the skin because they may have some plasticizers in there. And I think over time, there might be some generic groundwork effort to start to look at some of the more materials issues that people can buy for their home printers.
I've heard in the last couple of years about efforts to make houses with 3D printers, and I had heard that ideally the object was to make more affordable housing. But by your explanation of things, and it's understandable that with the pricing curve going down, how would you accomplish more affordable housing in the future using 3D printing?
I think that in the low cost, like for example, in the shelter, when we have earthquake or some other disaster happen, the low cost, the housing could make it affordable. The reason is we use a little bit lower cost material, and because robotic arm, we deposit the material can be fast. You do not need so high accuracy like biomedical implant, right? You need really high. It might be 50 micrometer or 20 micrometer. For the house, really might be millimeters. They can surface roughness we are fine. That's for the low cost one. So in that case, the speed use that robots, right, to handle the deposition, that will be low cost and fast. So if the material also can be in some way, let's say biocompatible, I think it can be very useful for low-cost housing. For the high-end housing, I think it might be a lot worth it because we could use some other means to make it better.
But also, I think what's to add in there is like if you talk about larger scale buildings, like how much money at the moment runs into making formwork to cast concrete in all sorts of complex shapes. So there's this 3D printing methodology called contour crafting, and actually that works with concrete 3D printing on a larger scale to actually realize super complex geometries which cannot be done or aren't affordable right now. So I think there's also in the design point of view an advancement in that sense.
She's the expert in the house. Okay, so.
And that's a really interesting comment, because whether you make a block that's 5 by 5 by 5 or a block that's extremely intricate, to the 3D printer, it doesn't matter.
Yeah, and there are also the companies who, like structural engineering companies, looking into how to make advanced joinery for like earthquake buildings. Like how can you make joints to actually move with the building, and how can you, because you can actually 3D print with combining different materials, you can actually have prints which go from hard to soft within one materiality, and they can sort of react on structural forces. And there's a lot of research in the building industry in 3D printing as well, not only on the full scale 3D printing of a house, but how to print maybe specific components within the building structure.
Yeah, here I'd like to add one thing that because we talk about go to Mars, right, in 2030 or something, so there is a strong motivation for NASA and also researchers try to bring robots in the future to the Mars and use the Martian soil, right? We just build a house there. So use 3D printing method. Hopefully that will become reality. I don't know how the house will become, but it's doable.
How were those titanium parts made? Were they layer by layer, and were there gradations in the titanium hardness and things?
Do you mean do you mean the titanium medical implants?
Yes.
Yeah, they're used, or they're made with a process called selective laser sintering, where you basically have a bunch of metal powder, and then a laser sinters every atom of that metal together. So they're sharing it basically kind of melds each particle to the neighboring particle.
Yeah, that's one way. Another way is to use electron beams. Because titanium alloy is to go to human body, you need a high purity, and really do not like get any oxide there. So basically, we use vacuum, high vacuum, and then shoot the electron beam. The electrons that flow almost like light, right, to melt titanium particles, microparticles, fuse them together, then layer by layer. By this way, you can build any shape you want and high density. So also, in the same way, build titanium, the aerospace, that kind of structure, also under testing. So, yeah.
For non-medical devices, medical devices have a intricate end-to-end control between the designer and the practitioners installing it. But for things like fashion or toys or any other medium-scale object, what are your thoughts on the intellectual property protection of where the real expense and ingenuity is, which was back at the design stage, versus a proliferation of gadgets that will print out a cloned copy of the files, destroying the basis of an industry the same way as piracy does with DVDs and books and other abstract digital files?
Well, I think I was just waiting for that question, so I'm really glad that you asked, especially when it comes to certifying like material, the question before, like for designers, it's like a huge question because of ownership and copyright. So as of now, in the fashion design, what I can say is that the network of the 3D printing companies who can actually 3D print in that scale with those materials is very narrow. So there are about, let's say, maybe 3 3D printing companies in the world who can actually 3D print with those materials in this scale. So right now. So I get a lot of these questions like, can I print this fashion piece at home? Well, now not yet, because you need the large-scale 3D printing machines, and you need actually the expertise of how to produce such a piece. And then you need the designer who is actually designing that. So at the moment, when you give out the 3D printing file to the company, you sort of have contracts whatsoever that don't allow them to give these 3D print files anyone else. And right now, no one else can print it. But there are certain designers who actually benefit from that, and they are making their files available online, so you actually go online and you buy the file, and then you can 3D print your piece at home. So it's sort of like you would go online and you would buy the music so that you can listen to it at home. But of course, there's a lot of open questions on how that actually will be managed with copyright if someone steals the file.
Julia, Professor Lee, Stephanie, thank you so much for a very inspirational and informative evening, and Dr. Wu for putting this. And now we have a reception outside. Okay?
Thank you.